A little bit of grade 11 reminders. If you're sitting on a bathroom scale, and we call somebody person number 1, and we call another somebody, actually, you know what, let's just have like this other somebody come along. And we'll give a body to them, so they're not just a nebulous somebody. Okay? And this other somebody, while you're trying to, and this happens with me with my kids, they'll walk in at me at the weirdest times. But let's just say that I'm on the bathroom scale, and some little helper, some little friend comes along, person 2, and the friend pulls you. Actually, let's make it be a nicer friend than that. Let's say that our friend lifts us. Come on, pick you up, you know? A little encouragement. Friend lifts us. Now, they're just a little friend, so they can't really pick us up off the ground, but they do try to give us a little hug and a lift. We'll give ourselves a reference frame. I can't believe I'm saying this already. I just got these markers and they're drying out, so I'll switch over to another one. We're going to up, down, and I'm not even going to write left to right because this is a one-dimensional problem if we're just lifting somebody. So I'm just going to forgo that one. And if we do the free body diagram for the person that's on the bathroom scale, we might have force due to gravity acting on person 1. We've got force of 2 acting up on person 1. Of course, I know off to the side there'd be a force of 1 pushing back down on 2, pressing my friend into the floor, right? But they'd be attached to 2 separate bodies. This is the person on the bathroom scale, this is the little friend, okay? So we're gonna ignore the little friend. And then what else am I missing? Yeah? There is some normal force, yeah. And I've tried to be good. I tried to make my F2 on 1 small. I think I didn't quite achieve it. Looks like the sum of F normal 1, F2 on 1, and FG on 1 should add up to being 0. And I should have made my FG on 1 a little bit longer if I was going to do that sort of graphically to scale. But the point is that all of this ends up being F net 1. Now, recently we just talked about statics. And so this actually is like a very basic static situation. This person sitting on a bathroom scale, what does it mean for the net force if the person's just sitting on the bathroom scale? What's that? 0. Net force is 0. So then we could say, hey, got a net force here? Yes, but it is 0. And remember, every time we do an FBD, it really is just like a visual for how to build an equation. So we have F net on 1 equals force of normal on 1 plus Fg acting on 1 plus force 2 acting on 1. And based on that idea of statics, F net 1 should be equal to 0. Our experience in the bathroom tells us we don't crash through the floor, except in extreme circumstances. And really this normal force here, maybe I'll even make a statement. The normal force is told to us by the bathroom scale readout, or dial, or whatever it is that you'd like to call it. So then we could get F normal all by itself. And really, hey, in the past, we've done something, we've been playing around with this, using negative signs at the equation building stage of things. If I wanted to go back here and talk about which items are negative and which items are positive, I could talk about FG1 being negative and all the other ones being positive, or I could wait until I sub values in to deal with the positives and negatives. I think this time I'm going to wait till I sub values in. And so I could say F normal 1 is equal to negative Fg1 minus force of 2 acting on 1. And I don't have any values yet to sub in. Just a side note here, that Fg acting on 1, that's the weight. That really is the weight. F normal acting on 1 is what you might call the apparent weight. The apparent weight could change depending on the scenario. And sometimes that weird little glitch of the wording shows up in a textbook question or something like that. So I just want you to know that when somebody says, what's the apparent weight, they kind of mean what the normal force is. What's the weight? Well, that's just Fg. Fg is always the weight. Okay? So apparent weight is kind of an odd thing to say, but really they're asking for the normal force. So maybe let's just make a little note to ourselves. F normal on 1, the apparent weight. That's what the readout would be on the bathroom scale. Other little side notes. If I was not talking about the rider, if I was talking about the elevator, sorry, if I was talking about, oh my goodness, if I was talking about having a generalized free body diagram, sorry, I could say, hey, I've got these couple of forces here. If I really wanted to have F normal as a generalized equation, this one's a really easy one. F normal is equal to negative mass times acceleration due to gravity minus force 2 acting on 1. That one's an easy one. What I want to do next is I want to talk about something that's a little bit more complicated, one where we don't go anywhere. And notice we haven't subbed any values in here. I have full trust that you guys can sub values into this, so I'm not even going to really bother with this. I want to go back up here to this elevator. Sorry, that's where my mind was going next. And I'm going to give myself a little bit of a boundary just in case I need to wander a little bit. And I do want to, because we've talked about elevators before. Yeah, of course. Let's give this one a nice simple acceleration. 2.00 meters per second squared upwards. So this is when the elevator just kicks into action. We'll give ourselves the same reference frame. We'll call it up, positive, down, negative. And we give this person in the elevator, just the person, mind you, 50.0 kilograms, because that would be a really low mass for a whole elevator. AG is equal to 9.81 meters per second squared, down. And if I were to do a free body diagram for this one, there's no little friend trying to lift this, looks like some sort of a business person, up. So I've got Fg, I've got F normal equals F net. I'm not convinced that I've drawn this to scale. What should be true about F normal relative to Fg if the person's accelerating upwards? Should be bigger, right? Yeah, F normal should be bigger. So that's a should be. I'll keep that in my mind's eye for a minute. But if I was going to turn this into an equation, I could say, all right, well, F net is equal to, well, F normal plus Fg. You know, maybe this time I come along and I do want to put a negative sign in, because there's one thing going up and one thing going down. Maybe I want to say, hey, I want this to be a minus sign. Maybe I'll rewrite that again. Maybe I'll say, okay, based on reference frames, F net is equal to F normal minus Fg, based on reference frames. So I'll just say for RF, for reference frame. I say, okay, well, let's see if I can get the F normal all by itself now. I'll take the Fg over to the other side, and I say F normal is equal to F net plus Fg. We've done this before. Part of what I want to do with this is talk about generalized equations again, just make sure that we can do this, because I feel like we need to nail this thing down. This is something we can't walk away from if you're in the minority of people that haven't tried to do a generalized equation yet. F normal is equal to mass times the acceleration of the system plus Fg, mass times acceleration due to gravity. Really, we could factor out the masses. Mass times acceleration of the system plus acceleration due to the gravity. And we could sub in, and we have enough numbers here, we could just plug these guys in. It's 50 kilograms times acceleration of the system, 2.00 meters per second squared. I got to be careful right now. When I add on the gravity, should it be negative or positive based on what I've done beforehand? Positive, right? Because I've already dealt with the negative sign back in the formula. So plus 9.81 meters per second squared Somebody with a calculator. It's really, look at this. 2 plus 9.81, 11.81 times 50. What's the F normal on this person's feet? Should start with a 5. Yeah.
590.5.
Nice. Nice. And up, right? So we could round that off to, it looks like it's only going to be 3 sig figs. Yeah. Was it 590.5 and then change, or exactly 5? Oh, this is like one of those weird significant figure rules where it ends in a 5 when we're rounding away the 5. So it actually has to go to 590 for 3 significant figures, because you round even when it's a 5 and that's all you get rid of, right? And that hardly ever happens. But up. Yeah. Honestly, if I got a generalized equation like this, any future elevator rider, I could figure out their normal force. It's a tool I can whip out of my tool set anytime. Now for us, because we have a variety of questions that are always being thrown at us, like we're master puzzle solvers or something like that, it's not as helpful. But you can imagine in the day-to-day life of being, the engineer or being the theoretical physicist or whatever, there are going to be a lot of things that are just like repetitive. And it's nice to, if you can make a generalized equation like this, not only cut down on your repetition of having to drive it all the time, but also, honestly, a lot of us are going to have some coding skills by the time we get into, like, even now, or by the time we finish first, second year university. We should be able to whack something like this into software and have there be like data entry fields where we could just like pop this into data entry fields in a basic software, or we could generate a spreadsheet where we could just pop this into certain columns and it would kick out an answer. So generalized equation isn't, I know that's like an over-explain, but does it make sense? Yeah. It's not because I just think it's cute or something like that. It's because it pays off. Unless you're going into medicine. And I know you are, so. Anyway, in which case it's just a puzzle. And that's okay too. Sometimes things are just puzzles. If I wanted to step back a second and say, hey, I'd like to think about this thing as a whole system. Seems to me that we might have to say, hey, there is a whole system here, not just the rider, but like there's an elevator involved. And so if there's a whole system, we could say, hey, there's an applied force being, I suppose, probably supplied by a motor. So let's just grant that that's probably some sort of a motor, whether it's electric or whatever, almost certainly electric. We'd have the mass of the elevator. We'd have the mass of the person. We could talk about there being an acceleration for the system. Of course, we'd have an acceleration due to gravity. Would you believe in an elevator there's probably friction somehow? Like maybe this thing's rubbing on the sides of the elevator. You could even have, I'll throw it into friction, but honestly, there's actually drag. Drag is a real issue for elevators. And you notice those little holes that are in the elevator doors, and when the elevator is moving, air either gets sucked in or drawn out of the little holes in the elevator doors. If you haven't noticed them, they often have like a little chrome grommet or stainless steel grommet around them. Put your hand over the hole just for a second. Just feel the flow of the air. It's because this is a giant piston that's going up and down, right? An elevator is a giant piston that carries people. That's kind of what it looks like from the outside. And so we actually do have to have pressure relief out of all those little holes. So I'm going to call it friction, but I'm going to recognize that drag's a part of that. Like it's plowing through air that's got to get pushed out through those holes or elsewhere. And then if I was going to think about these masses, these accelerations, this force, don't forget there's Fg associated with that Ag. Then I might say, hey, there's this mass of the system equals mass elevator plus mass of person. But if I wanted to go and find the acceleration of this system, I would do something like acceleration of the system equals F net over the mass of the system. Well, in this case, the F net for the system would be F applied, the motor, plus Fg, and I could even say it's Fg acting on both the person and the elevator, plus Fk, all divided by the mass of the system. And I've kind of painted myself into a corner here. So I'm going to do a cheat. And you can take your finishing line to this up to the margin of the page, but I'm going to cheat by just laying down a piece of stick-it note here, because I get to do that. And if I wanted to take the acceleration of the system and generalize it further, I could say, well, the applied force is that motor. I can't generalize that any further. The Fg, however, is going to be acceleration due to gravity times mass of the elevator plus the mass of the person. And then I'm going to leave Fk as an experimental value because it would involve some sort of coefficient of friction of rubbing on the side of the elevator plus whatever the normal force is on the side of the elevator plus a fluid dynamics issue of the fact that these elevators actually plowing through air, so it ends up being a bit of a fluid dynamics drag issue. So I'm just going to leave that all as Fk, and then the mass of the system would be mass of the elevator plus the mass of the person. And the nice thing about something like this is, you're asking what's the point of having a generalized equation. I've got a few variables that I could plug into this thing, and I wouldn't have to keep on deriving this over and over and over again, right? That's nice. Now the thing about the Fk thing is that if I am going to have drag on there, drag is speed dependent. So I would really have to unpack this even further to make this even more generalized and talk about how the cross-sectional area of the elevator is going to have to relate to the speed at which it goes as it plows through air particles. Like, it seems so silly. Like, it seems like this is going to be a simple problem, but if you want to truly generalize it, it's a little bit of an unpacking process. And I guess that's one of the reasons why we talk about generalized equations too, is to really get down to the nitty-gritty and see it all in one place,